other hierarchy. So this side, the left side is the abstraction hierarchy, and the right side is the implementation hierarchy. But then why is the name bridge given to this pattern? The name bridge is given because this pattern provides a bridge between the abstraction hierarchy and the implementation hierarchy. So this is the abstraction hierarchy, where the terms line, rectangle, etc., these are invariant with respect to the specific implementation, whether it is a desktop, whether it is a smartphone, whether it is a embedded application, whether it is a animation. We still call those as line and triangle because these are application domain terms. On the other hand, on the implementation domain terms, we have high resolution, low resolution, transient view, and so on. So this pattern separates out the abstraction hierarchy from the implementation hierarchy and provides a bridge between the abstraction and the implementation, which is basically a association or a aggregation relation, which helps the application class to invoke the methods of the implementation class. We can redraw the structure like this, the same one. Here the abstraction is a abstract class, and many operations are defined. The refined abstractions are concrete class. These are application domain classes. The client invokes the abstract class here, to which the corresponding concrete class is bound, and then the implementation is an interface, and depending on the type of platform and so on, there are different implementation classes here, and the correct implementation class should be bound to the abstraction. If we look at the participants of this pattern, we have the abstraction, the refined abstraction, which are basically concrete classes in the application domain. The implementation is an interface, and then there are concrete implementations, which are basically classes defined on platform variations and so on. The abstraction defines an abstract interface which the client uses, and it maintains a reference to the implementer, and that's how the bridge is established. The refined abstraction is a concrete class which extends the interface defined by the abstraction. The implementation or the implementer, this defines the interface of the implementation class, and the concrete implementer are the concrete classes which are implementation specific, and they implement the implementer interfaces. Here, as the client invokes a method on the abstraction, it may do some work and also, if necessary, forward to the implementer object, the correct implementer object. The clients only interface with the abstraction class, they don't interface with the implementation class, and the abstraction class forwards any request to the implementer class. Let's take a few examples to understand the applicability of this pattern. First, let's look at a window example. In the window example, let's say we had two window types, the Microsoft window, MS window, and the Mac window. But then after some time we had the need for icons, and we defined a special type of window called as icon window. But then the icon window must be implemented on both the MS window and the Mac window, and therefore we subclassed the Mac icon window, made it MS icon window and the Mac icon window. And similarly, we might have other platforms, for example, Android platform, and then we not only add a class here, Android window, but also we will have to add the Android window here. Similarly, Unix window we will also have to add here. So each time we make a change, we make multiple class additions are required. There is a single class hierarchy, and we have not separated the abstraction from the implementation. That is the problem. We have not used the bridge pattern. To be able to use the bridge pattern, we must identify what is the abstraction here and what is the implementation. The abstraction are the different types of windows. For example, the icon window, the application window, these are the different types of windows, and their implementation, whether it is in the Microsoft platform, Mac, or maybe the Unix platform, Android, and so on, those are the implementation. If we consider that, then the application of the bridge pattern becomes very simple. We have the abstraction on the left side. There are two main types of window concepts. One is application window and one is the icon window. Each icon has its own window, and the application window has many icons and other things. So this is one type of window, and this is another. These are two basic types of windows. But then these can have implementations on various platforms. So we have the window implementation, that's the interface, and we have various implementations of the window implementation, that is Microsoft window implementation, Mac window implementation, Android window implementation, Unix window implementation, and so on. So we have separated out the abstraction hierarchy from the implementation hierarchy and have successfully applied the bridge pattern. Now let's look at another example. We are given this hierarchy which some designer has come up. So he has the thread scheduler class here, and then he subclassed it into preemptive scheduler and time slice scheduler. And then there is the Unix preemptive thread scheduler, the Windows preemptive thread scheduler. There are two types of preemptive thread scheduler, one for the Unix platform and another for the Windows platform. Similarly, for the time sliced thread scheduler, we will have two subclasses, the Unix time slice thread scheduler and the Windows time slice thread scheduler. But later, as maintenance was required. It was used for some time and then new requirements arose, and then we need to support the Java platform. And once we tried to support the Java platform, we saw that we not only should have a Java JVM preemptive thread scheduler, but also the JVM time sliced thread scheduler. So the hierarchy becomes more and more complex as new changes occur to either the abstraction or the implementation concepts. We need to apply the bridge pattern, separate out the abstraction and the implementation and provide a bridge between that. Now, what is the abstraction here? The abstraction are the different types of thread schedulers. It's very easy to see here, a simple example, that there are two basic types of thread scheduler. One is the preemptive scheduler and the other is the time slice scheduler. But then their implementation is different on different platforms. For example, Unix, Windows JVM. So these are the implementation domain and this is the abstraction domain. If we separate that out, we have the implementation hierarchy, the abstraction hierarchy on the left side and the implementation hierarchy on the right side. The number of classes has reduced, and not only that, if there is a change on the abstraction side, we have a new scheduler or we have a new platform, we just make small change to the corresponding class hierarchy. We don't need to have too many subclasses added for just one simple change. Now let's look at one more example. Okay, before that, from our examples, let's make some observations. If an abstraction has several implementations, that is, we have defined some abstraction ideas for application, but then it can be used on various platforms and so on. And then the programmer is typically tempted to use inheritance to solve the problem. Just add some classes in the inheritance hierarchy. But then the problem that occurs is that the inheritance binds the implementation and abstracts together permanently. And it becomes very difficult. The solutions are too complex. Any small changes require too many changes. But then what is the design principles? Does this kind of solution violate that a programmer for any small change that is on the abstraction hierarchy or the implementation hierarchy just make subclasses on the same class hierarchy? If you look back to the previous lectures, you will see that it violates the single responsibility principle. Violates the single responsibility principle. Now let's see what a programmer had to tell as he became more experienced and observed what he has been doing. He had this to say. He said, as a beginning object-oriented analyst, I had a tendency to solve the kind of problems by using special cases, taking advantage of inheritance. I loved the idea of inheritance because it seemed simple, new and powerful. I used it whenever I could This seems to be normal for many beginning analysts, but it is naive. Given this new hammer, this new tool somebody has learned, very simple tool, everything seemed like a nail. Very correct, and that's how many of the application solutions become complex, because of the overuse of inheritance, tend to violate the single responsibility principle, and must keep in mind the bridge pattern and make use of that. And given a ugly design, we should be able to refactor by using the bridge pattern. We must use the bridge pattern when we want to avoid a permanent binding between the abstraction and implementation. Also, the implementation may be selected and switched at runtime, so the application can run on different platforms seamlessly. Both the abstraction and their implementation are extensible without implementing the clients. Even the code need not be recompiled. Now let us look at another example. Let us look at the circle shape problem. The problem is that we have a circle, we have a package where we can draw a circle, and also we can do various manipulations on the circle. For example, we may stretch it, we may contract it, we may change the color, we may change the fill pattern, and so on. But also the circle can run on the browser, the circle can be displayed on the browser, on a standalone application, on the mobile phone, and so on. It's again a straightforward application of the bridge pattern. So here the abstraction and the refined abstraction is the shape, circle shape, and the concrete circle shape, where we can have various operations like resize, change fill pattern, change color, and so on. And then the implementation hierarchy, where we have implementation on web browser, smartphone, and so on. So here these are the classes which participate in this pattern: the abstraction, which is the interface; refined abstraction, which is the concrete circle class; then we have the implementation, which is the interface; and then the concrete implementations, which use different drawing APIs for different platforms. Now let us try to see the code, the Java code. Here on the implementation side, the drawing implementation is an interface. It only supports draw circle given the center and the radius, x, y, and the radius. It can draw it on a web browser, that is one implementation. Another is on a smartphone, another is on a specific application, and so on. So this is the simple code for the interface drawing implementation. And then we have the concrete implementations which implement the interface drawing implementer. So we have the concrete implementer A implements the drawing implementer, and here for each of the methods in the interface we provide the definition. And similarly for the other concrete implementation we have the implementation for the draw circle. Now let us look at the abstraction hierarchy. Here we have the interface shape. Here we have the abstraction domain terms or the application domain terms like draw, resize, change fill color, fill pattern, and so on. Now this is a simple interface shape. Now let us look at the concrete shape, which is the circle shape. Circle shape implement shape, and then it has the constructor where we provide the specific concrete implementation. The drawing API is an argument on the constructor, and that is how the bridge is established. And here in the private drawing API, we store the argument provided in the constructor. And then we have the other application specific, abstraction specific methods. Wherever required for implementation specific methods, we call the method of the class, specific class on the implementation hierarchy. Here we are calling the drawing API.draw circle, which is the drawing API is the implementation class, concrete implementation class, and we are calling the draw circle on that. Whereas the other methods are on high level abstraction specific methods. For example, resize by percentage, change fill pattern, change circle color, and so on. Simple code example for the bridge pattern. Now this is the client code. In an array, we create many circles. 2 circles we have created, and we have given 2 different APIs for those 2 circles. And the client just interfaces with the abstraction domain class, which is the shape, and then we call the shape resize by percentage. It will be handled by the method in the abstraction class without really invoking a method on the implementation class. Whereas we might also invoke, the client might also invoke some methods which will require calling a corresponding method on the implementation hierarchy. Wherever there is any change request, they just use the inheritance to define a new class. Has its problems. Unless we are careful, it can bind the abstraction concepts to the implementation concepts and make the application extremely complex, and there will be a rapid increase in the number of classes in the application. And therefore, everybody who is concerned with object oriented software development must know the bridge pattern well. It helps to avoid some of the major problems in object orientation, in specific violation to the single responsibility principle or the SRP. Now let us recollect the class structure of the bridge pattern. In the class structure of the bridge pattern, we have the abstraction hierarchy, where we have the abstraction as abstract class, and then we have the concrete abstractions, and these are typically named from the application domain terms. The client invokes services on the abstraction, and the operations may be fulfilled by this abstraction class, concrete abstraction class itself, and if necessary, it will delegate to the concrete implementation class, and this is the implementation hierarchy, and this is the general structure of the bridge pattern. Now let us try to solve one more problem and see how we can apply the bridge pattern. Okay, this is already there in most of the applications. If you try to understand the application code, you will see that every database application where we have the application level classes, they have a bridge to the ODBC implementation. The ODBC implementation is subclassed into various types of databases, the DB2, Oracle, Informix, and so on. And this helps us to separate out the implementation hierarchy from the application hierarchy. Now please try to do one exercise. Let us say a programmer was employed in a vehicle sales showroom, and then he was trying to have this application developed to keep track of various vehicles that the company deals with, the showroom deals with, and then how many units are sold and so on. His main class hierarchy that was used in the application looked like this, that the car are different types: Ford car, Toyota car, sports car, and a truck is a special type of car. The SUV is also a special type of car, and then we have the Ford and the sporty model, the Toyota truck, which is subclassed from the truck and the Toyota, the Ford truck, Ford and truck, and the sporty Toyota, which is a subclass of the Toyota and the sporty, the Ford SUV, which is a subclass of SUV and Ford. And as the number of models increased, this became much more messy, very complex, violates some principles, object-oriented principles, makes the design extremely complex to understand and maintain. Now this is a candidate for application of the bridge pattern to simplify the design. But the problem that we are posing before you is that how do we exactly apply the bridge pattern here? We know that we will have to apply bridge pattern, but how exactly do we apply the bridge pattern? Where is the abstraction hierarchy, and what are the implementation hierarchy? If you think enough, you will find that the things that are on the abstraction side are the different types of cars, maybe the sporty truck, SUV, and then these are the ones that are manufactured by different vendors like Ford, Toyota, Maruti, and so on. So on one side we have the abstraction, the same sporty may be manufactured by Toyota, by Ford, by Maruti, and so on. So we need to separate out the abstraction hierarchy from the implementation hierarchy, and that's what we've done here. Applied the bridge pattern. We have the car models, sporty, truck, SUV, and so on. This is the abstraction hierarchy, and on the implementation hierarchy we have the car manufacturer, the different companies: Ford, Toyota, Maruti, and so on. Now few concluding remarks on this pattern. We apply the bridge pattern when we want runtime binding with the implementation through an association relation and delegation of responsibility. If we don't use the bridge pattern, we will have a permanent binding through inheritance. It's not a runtime binding, but a permanent binding. And the bridge pattern helps to overcome proliferation of classes. And to apply the bridge pattern, we must clearly understand the two orthogonal class hierarchy, what are on the abstraction hierarchy and what are on the implementation hierarchy. That requires some understanding of the problem, and we can see that what exactly is the abstraction hierarchy and the implementation hierarchy. One of the issues is that when a request comes to a abstraction class, it needs to delegate to a concrete implementer. But then there are many types of concrete implementers on the implementation hierarchy. So which one does it delegate? In our code example, if you see that we had stored the specific or the required implementation class when we created the abstraction class. Through the constructor of that, we had given the reference of the implementation class. So that's a simple thing to do, a simple way to identify which is the implementer class method which will be invoked. And the bridge pattern helps us to find what varies and encapsulate it, and it helps us to favor composition over class inheritance. It has many benefits, decouples the abstraction from the implementation, reduces the number of subclasses, reduces complexity and the code size. The different concepts in the interface and implementation can be varied independently without affecting the two hierarchies together. So if we vary the interface or the abstraction hierarchy, only the abstraction hierarchy will vary. It should not affect the implementation hierarchy. And similarly, if we have a new implementation, it should only change the implementation hierarchy. It should not affect the abstraction hierarchy. And it makes it more maintainable. But are there any drawbacks of this pattern? Is there anything or any consideration on which using this pattern we are a loser? We sacrifice some benefits. If we really think about it, okay, increased complexity, don't agree to that. I think it reduces the complexity. But possibly indirection, that we have to store a reference to the implementation class and invoke its method. If we really think of it as a drawback, possibly that can be a drawback, that it is an indirection. But I don't think that these are really big problems. Now let's look at the proxy pattern. The proxy pattern is also a frequently used pattern. And one of the important things of this pattern is that this same pattern we use for various purposes. We'll outline about a dozen purposes for which the proxy pattern becomes useful. And no wonder that this is also one of the very frequently used pattern. Any programmer is developing a application of some size would have opportunity to use the proxy pattern in his application development. Now let's try to understand the basic idea of this pattern. This is called as a proxy or a surrogate pattern. Here we have an application where there is a server class and whose methods are invoked by various client classes. The server provides service to many clients. But the problem that we are trying to address in the proxy pattern is that how should the clients invoke the services of the server when the access to the server should be managed in some way. For example, only some clients should be able to execute some methods. Some clients should be able to change data, others should only read data, and so on. The solution provided by this pattern is that we have to create a proxy object on the client side. See here, we have several objects created on the client side, the proxy objects. These proxy objects can help to do various things. For example, they can help to authenticate. Only a client who can invoke some specific method will be allowed to invoke that method, otherwise he will be denied, lack of permission. The proxy can hide network operations such as determining the server address, communicating with the server, establishing handshake, obtain server response, seamlessly pass that to the client, etc. Basically simplifies the client side design. It makes many things, it takes responsibility of many things, and the client just delegates those responsibilities, and the client seamlessly contact the server as if it is on the local machine. They hide the details of the network operations. And there are many other roles of the proxy, as you will find out now. Before we discuss the nitty-gritty of the proxy design pattern, let's just try to understand what is the role of a network proxy server. Anybody using a internet will definitely be aware of the network proxy server. Why do we use a network proxy server? In what ways does it help? If we can answer these questions, then we will see that this has some analogy with the proxy design pattern that we are going to discuss. The proxy, in the proxy design pattern, also has similar responsibilities like the responsibility of the proxy server in a network. Let's just identify the responsibility of a network proxy server, even though it appears as a digression, because that's not our focus in this course to discuss about networking issues. But then if we can know the responsibility of a proxy server, that will help us to understand our proxy design pattern better. A network proxy server has various responsibilities. The first is to keep machines behind anonymous. They have private IPs. The machines behind the proxy have private IPs and they are anonymous, mainly for the security, and also it helps to handle the problem of providing enough number of IP addresses. it helps the machines behind anonymous and the outside world. They basically need to contact the proxy over the network, and then we will have firewall and so on, and therefore the computers behind the proxy are safe. Another important role of the proxy is that they cache resources. As the different computers on the network, they access resources on the internet, various servers, they get resources. These are cached here. For example, a user accessed a news item that is cached here, another user trying to access the same news item. Don't need to really go over the internet and again fetch, it's available, fresh news item, and that will be given without really having a multiple accesses over the internet. It prevents downloading the same content multiple times and saves bandwidth. This is basically the caching, that because of the caching we provide fast access. If it is cached here, we not only provide fast access but also we save bandwidth. It can log uses. What are the users and what sort of uses and how much bandwidth they have consumed. There can be a log of that, and this can be provided to the company management on employee-wise internet uses. We can have a firewall associated with the proxy server to scan for malware. Also, the encryption and SSL acceleration, the secure socket layer encryption, is typically not done by the web server, the web browser. Otherwise, it will really slow up if we do the SSL encryption on the browser itself in software. Rather, we will have a hardware acceleration installed in the proxy server, because all requests to the internet goes through the proxy, and therefore the hardware acceleration, hardware SSL acceleration, etc. can be provided on the proxy. Load balancing. As an external request comes, when we have multiple servers behind the proxy can do some kind of load balancing and find out the server that is less loaded, can forward the request to that. Compression. Proxy server can optimize and compress the contents before transmitting it on the network. Spoon feeding. Sometimes some of the clients are too slow, and if the server dumps the response on them, they will be overwhelmed, and the proxy basically spoon feeds them as it determines the slow clients. As you can see that a network proxy server has many responsibilities, and similar is the case with the proxy design pattern. Now let us look at some of the ways in which proxy can be used. We use a proxy when the services provided by a supplier needs to be managed in some ways without disturbing the client interface. The supplier interface. So we have a supplier or the server, and we want to manage it some way. Maybe authentication, maybe unless we really can have to invoke the server, will not allow it, and so on. These basically the proxy helps to implement some additional conditions to be satisfied before the server object is accessed. Let us say we have various pictures displayed here. These basically are the proxies. If you click on a picture, it will show the picture. It is not showing now. As you click, it will load only that picture at that time once you request it, because there may be thousands of these, and if you load all of them, it will be very slow. So, load on demand. The proxy takes the responsibility that when a client is interested in a specific picture, it will only show that. Now, let us look at the pattern. Here, we will have a proxy object created that will have the same interface as the target object or the server, so that the client would have no way to know whether it is dealing with the proxy or the target. The client may be under the impression that it is directly invoking the target, but it might be dealing with only the proxy. And the proxy should store a reference to the target object or the server, and whenever required, a client request comes and the proxy cannot handle it, it will forward it to the target object or the server. But sometimes it just does not forward it as it comes, but it does some pre-processing, then invokes the server, and then maybe doing some post-processing. So, basically the proxy can help us to wrap code around the reference to a server. The client would interact with the proxy. The proxy can answer many of the queries of the client, or it can provide service, many of the service requests it can handle itself, and some it may forward to the real object or the server, but then it may wrap some code around it, it may do some pre-processing and post-processing steps. So, those are the roles of the proxy. It is a structural pattern. It provides a surrogate for some object. So, the object, actual object or the server may be in a different machine or across the network somewhere, but the client won't know it, because the proxy will be co-located with the client, and the client would be under impression that it is interfacing with the real object, even though it is only interfacing with the proxy. And the real object or the server may not be instantiated. The proxy will determine when to instantiate the real object or the server, and that will help us to speed up the application, give improved performance, and also provide location and access restrictions. Now, let us look at the first uses of proxy. Help reduce expensive steps in an application, so that the application will get speeded up. Now, if we analyze the application and find out what is expensive, we will see that it takes time to create heavyweight objects. For example, if you have to read 50 megabytes of data to create an object, a picture object or something, it is definitely time consuming. Similarly, object initialization for the heavyweight objects, these are expensive. And to speed up the application, we should create this and initialize this only when needed, because there may be thousands of such objects and maybe in a typical run maybe just couple of them need to be created. Why should we create thousands of them if we can determine which one or two are to be created and we just create only those? So it helps us to defer object creation and initialization to the time the object is actually created, actually needed. We don't have to, at the beginning of the application run, we need not create all these heavyweight objects. The proxy will help us to create and initialize at the runtime only those which are actually needed. This will help to make the application work very fast. This will help as if the application is working very fast. And many of the applications actually do use this technique. The proxy pattern reduces the cost of accessing objects, and the proxy objects act as a stand-in for the real object. We will see with the help of some concrete examples, and we will name the different types of proxies that are used in typical applications. At least we will identify half a dozen or so. Of course, there are more uses of the proxy pattern, but we will identify some of the important uses of proxy pattern. We will give the class diagram, the class structure for the proxy pattern, so that given a situation, we should be able to create the proxy pattern solution to handle the problem. We are already at the end of this lecture, and we'll stop here. We'll continue with the proxy pattern in the next